Greetings and welcome to today's lecture. As you can see, it's going to be on atmospheric humidity and condensation. This video lecture is not going to get through the entirety. You can see this also encompasses 2 chapters in your book, so we're going to get started on this today. We'll have an opportunity to ask questions as needed in class, and we will wrap this up as we work into next week starting on Labor Day. And so this first slide, we tease this in one lecture, but we're going to go through it briefly to make sure we're both on the same page here, both lectures. What are we going to be talking about as we work into humidity and condensation? The first and foremost thing is water is tricky. It is existing in solid, liquid, and gas, all 3 states naturally. So that is something that is not common to most materials on Earth. And also, as we saw previously with regard to how this can influence weather in the northern versus southern hemisphere, the majority of Earth is covered in water, almost 3/4. And so we're going to talk about this latent heat release that occurs when we change states, when we convert from a solid to a liquid, or also when we reverse processes, gas to a liquid, things like that. And some of these processes are going to be significant drivers of weather. In fact, when we take our gas and we convert it into clouds, we're going to start to see some interesting effects on what happens with the potential for severe weather. And so they can release or absorb large amounts of energy, and that's going to help to fuel those large cumulonimbus clouds that we see during severe weather events. And I'll motivate it slightly here with clouds are simply pretty. I would wager everyone here, whether they would admit it or not, has at least once or twice looked up in the sky, seen some neat clouds, and kind of said that cloud looks like whatever. And it's just one of those things we naturally do. And so we're going to talk about why we see different clouds the way we do and which ones are, for instance, concerns to us as humans and which ones are generally not any issue in terms of sensible weather here down at the bottom of the troposphere. And so we start off with the hydrologic cycle. Hydrologic cycle, the idea of all the water within the Earth atmosphere system and how it evolves over time, where most of it is stored, so on and so forth. And what we see here is the vast majority of the hydrologic cycle is contained within the oceans, 97%. A decent amount, though, is in ice and glaciers. That is something that overall has decreased in the last number of years, but still holding at about 2%. Interestingly enough, there's a substantially larger amount of water contained in the ground than there is in the lakes. But the most interesting thing in some ways here is the incredibly small amount of our fixed supply of water that is contained in the atmosphere. 97% oceans, 99 when we add in ice and glaciers, almost 100 when we add in groundwater. 0.001% is going to be a lot of what we focus on in this class, that small amount. And so you can see in a couple of our blue boxes the idea of PE ratio, for those of you studying things over in Urschel Hall, not price to earnings ratio, but comparing precipitation and evaporation. And not surprisingly, we see precip exceed evaporation over land and vice versa over water where the large sources of H2O are located. And so ultimately, we simply have evaporation occurring over the oceans, transported over the land. These will eventually condense into clouds, and we're transferring the energy within the Earth atmosphere system through these processes. And so again, talking about the phases of water, nothing earth-shattering here, the fact that we have solid, liquid, and gas. And the phases are going to be related to the speed of the molecular motion. Remembering back when we talk about temperature as the average kinetic energy of molecules, simply here we can see at the bottom, gas things are moving relatively quickly, relatively low density as well. Water, higher density, we may just have a little bit of small motion of our water molecules. And then ice, this almost look of a helical setup, and to where they're going to be very little motion to the molecules. So ice is going to be the coolest or the slowest phase, just a little vibration of our molecules. Whereas water vapor, things are bouncing around left and right. This is going to be our warm or fastest phase of water. And again, one of the things we're really going to focus on in the upcoming slides, as well as throughout the rest of the semester, to be honest, so this is good stuff to get a handle on, is what is going on with these phase changes. And so let's take a moment or two on this slide. Latent heat. Definition up top there. Latent heat is the heat energy that is required to change a substance from one state to another. For instance, if we change a liquid into a vapor, or we change a liquid into ice, it's going to have different effects on what is happening with regard to heat in the environment. And so all of the different things on this image at the bottom can happen. So usually we think about these four arrows happening here in the middle. We think of liquid evaporating into vapor, or we think of vapor condensing into liquid water. Ice melts into water, and water freezes into ice. Again, nothing earth-shattering here. We have two other things that are maybe a little less common. We have ice directly changing to a vapor, skipping over the liquid phase. Although not exactly with water, when you think of sublimation, dry ice often comes to mind. Frozen carbon dioxide that we don't see turn into a liquid, we simply see it turn into the vapor state. And then you have vapor deposing directly into ice. So if you wake up some morning this winter and you have some frost on your car windows, deposition was the cause. And so you can see all of these different arrows, but the ones at the top and the bottom are very critical. These are things that you should definitely keep in mind, and you'll have a chance to practice these in an upcoming lab. When we are working from the left side of the diagram to the right side of the diagram, heat energy is taken from the environment in order to make these phase changes occur. In other words, to move from ice to liquid, we have to pull heat from the environment for that phase change to occur. Conversely, if we move from right to left, we're going to be releasing heat energy to the environment. The one I'll pick on here is if we move from the vapor state to the liquid state. We have water vapor occurring in Earth's atmosphere, and sometimes through the process of condensation, we form clouds. When that happens, heat energy gets released to the environment, and this is one of the catalysts, as I've already alluded to, for severe weather if the other atmospheric conditions are good. And so again, these couple of blue boxes up here are going to be critical in helping you to realize what is happening with regard to heat in the environment. Is it being taken from the environment to cause the phase change, or through the phase change being released to the environment? And so if this causes you nightmares, I throw that to Professor Craig Clark. This is one of his archives. If you do not have Professor Clark for lab, you may already have heard of him. He really loves his snowfall. And so he has this, to be fair, kind of disturbing Frosty character, but I keep it in regardless because it is amusing in some ways. And so we have Frosty here with his hat bouncing up and down, his really low quality GIF hand waving at you, and he has a temperature of -3 degrees Celsius. In this environment, we're going to hypothesize, or we're going to set up the scenario, should I say, that his net incoming solar radiation, in other words, what's coming down and reaching Frosty, is exceeding what is outgoing from Frosty. In other words, he has a net positive amount of radiation. And so the question you should ask yourself for a moment is, what's going to happen to Frosty? Again, he's at -3 Celsius, but he's receiving more radiation than he is giving off. I'll give it a moment. Chances are good most of you have thought, naturally, Frosty will melt. And, well, that probably would be what I would guess up front, too. But in reality, he is going to warm. He's going to have to warm up to 0 degrees Celsius before he has the potential to melt. In other words, the heat energy is actually warming Frosty, not changing his phase from solid into liquid. But let's look at the scenario now where we've had enough incoming radiation to warm Frosty to 0, and the temperature, will say, just for argument to make sure this is meteorologically sound, is also at least at the freezing point. We're going to continue to add energy from the environment to Frosty to the point where the incoming shortwave solar radiation will exceed his net outgoing radiation. And what would happen to Frosty now? The answer is yes, Frosty will begin to melt. And so what's happening here, I should stop before I go to the next slide, is that we're going to add that heat energy to Frosty to change his phase from a solid to a liquid. It means that we're not actually increasing the temperature for a period of time. We're simply converting him from, well, a somewhat disturbing GIF into a puddle on the ground. And so this is another way of looking at things. This is a pretty important diagram as well. The idea of what's happening as we convert ice into a liquid into a gas, and we can reverse this process as well. And so we're going to look at this idea of latent heat. Here what I have circled is the idea of how much energy is needed to convert a liquid into gas. And so you can see the number there, 540 calories per gram is needed to vaporize water. This is again going to be the energy needed to cause that change. If we were to reverse the process, change the gas into a liquid, we would release effectively the same amount of energy to the surrounding environment. You can note that if we are trying to convert a solid into a liquid for water, we still require energy, but substantially less than we require in order to turn that liquid into a gas. In fact, it is a fraction of what we need, only 80 calories per gram. In many ways, it takes a lot less to cause some ice to melt than it does for water to boil. And this is evidenced in many ways by the fact that, yes, a watched pot never boils, as the old adage goes. It does take a lot of energy to get us into that new phase. I should stop and go back here for one more moment. You can notice that the temperature scale is showing that, again, at the point where we're converting from one phase to another, this 80 calories per gram or this 540 calories per gram that is needed to vaporize or melt is not going to warm the water. It is simply in the phase change. Thus, the horizontal dashed line during these steps at 0 degrees Celsius as well as 100 degrees Celsius. Evaporation and condensation. Evaporation, again, liquid to a gas, oftentimes referred to as vapor within our field. This requires heat from the environment. Again, this is a little reviewy from what I've talked about thus far, but these are very important terms that you should definitely have a handle on as we move forward throughout the semester. Condensation, we reverse that process, turn our vapor into a liquid. So here we got your glass with a bunch of droplets on the outside, likely pretty slippery as you pick it up, and the idea that you probably have a cold drink inside in a relatively warm surrounding environment. And this is going to release heat off to the environment. As I've already alluded to, these become quite critical when we deal with the development of thunderstorms, how much heat is being released to the environment, causing additional buoyancy in the atmosphere. Buoyancy being rising motion that aids in these tall, somewhat dangerous cumulonimbus clouds. Saturation. We're going to spend a little bit of time on saturation here in this video, and then we will jump into a little bit more saturation later on. Saturation is defined as an equilibrium between evaporation and condensation. Saturation, for the purposes of this class, MET 103, is effectively the most moisture that the atmosphere, or an object to be fair, can hold. What it means is that for every molecule that is evaporating away from this plane of water, another one condenses. The rates are equal. We're going to spend some time, both today and in lecture, describing what some of these terms are to describe whether or not the atmosphere is saturated. Some of this gets a little complicated at times and a little on the cumbersome side of things, but hopefully by seeing these videos and having some chances to experience these in class and lab, the concepts will become pretty comfortable. Evaporation gets a little tricky at times as well by the fact that it can be influenced by both wind as well as temperature. I alluded to this in class. You are on an 85-degree day, you go for a swim, and you get out of the pool, and you are actually cold. It's 85 degrees outside, but you're kind of chilly if there's a breezy day. The evaporative cooling effect is that water is near your body and evaporates into the atmosphere is going to, again, cause your body to feel chilly. These have some notable impacts on saturation. We'll talk a lot about temperature and the fact that, well, a muggy day in summer, you might not necessarily be close to saturation, but we can be saturated in winter when it's cold, and to be fair, we don't feel like it's muggy outside. And that's the effects on the human body as well. And so we're going to start here and we're going to take a break. Maybe we'll even take a break after this slide. We will, as I think about it. Measuring water. Understanding the amount of water vapor in the atmosphere is a very important thing. It's going to become critical as we talk about any number of things moving forward. Mid-latitude cyclones, hurricanes, climate change, so on and so forth are all going to be related to water vapor. In many ways, temperature and water vapor are the two variables that we spend the most time on throughout the semester. But what you will see in the upcoming slides is there are many ways to describe what's known as the humidity of the air. In fairness, there are many more than we discuss in this class, and we're going to focus our time on the ones that are most important at this level, and that includes ones that you will see on the nightly news or other things in a general weather discussion as you move forward from this introductory class. So no sweat if some of these are a little tough to get by, and we'll pause this video then for now and we'll pick things up in a little bit.